All right, last video for partial derivatives. I know there's been a lot, trying to be really thorough with them, so hopefully you're getting the basics though, right? Okay. So the next thing is just a little bit, you can have functions of more than two variables. So we've been doing functions of x and y, z equals f of xy. We can have, you can have a function of, a lot of times once we run out of x, y, and z, we just start calling them x1, x2, x3, x4, all the way to xn. Okay, so we could find a partial with respect to, x52 if we wanted to. Just treat all of the x's as if they're a constant. So an example of that would be, maybe we have a function in x, y, and z, which is e to the xy natural log of z. Okay, so we can take our partials. It's just you treat more than one variable as if it's a constant. So when I take my partial with respect to x is my independent variable, everything else is a constant. So natural log of z, that's just a constant. And the derivative e to the xy would be e to the xy times x, because of your chain rule. Okay, so we would have, times y, right? Think about it. If you have e to the 2x, the derivative of that with respect to x would be 2e to the 2x. Okay, so just think like that. So if that 2 were a y instead, we'd have y e to the xy, and then we still just have the natural log of z, because it's not a constant that's being added, it's a constant that's being multiplied. Very similarly, your derivative with respect to y would be x e to the xy natural log of z. Okay, and then one that's a little bit different would be your partial with respect to z. Exy is a constant, and the derivative of the natural log of z would be 1 over z. Okay, so it's the same process. It's just you have more variables that you treat as if they're constants. Okay, we can get to our higher order ones, which is just, taking your second, third, fourth partial derivative. Okay, so we'll see those written as something like fxx. Okay, what that means is, first you take your partial with respect to x, and then whatever you get from that, you take it with respect to x again, which means when we're talking about all of the second partials, you could have 4 different combinations. You could take it with respect to x first and then y. You could take it with respect to y and then y. You could take it with respect to y and then x. Okay, just make sure you take the first one first and then the second one. Other ways of writing that, I'll take one where they're different. That would be, you could write it as this. Okay, so that's a little more explicit that you do x first and then y. So is this one. Take the partial with respect to x first and then y. That's how we'd also get something like that. Or if it were fxx, that would be like that. Okay. That's pretty much, I'm just going to leave it like that for now. There might be some other notations, but these are the ones that you'll see in your book. Okay, so let's do some examples of those, because these get really fun then. Okay. Let's say we have this guy. You might want to, this would be a good opportunity for you to pause and make sure you can come up with your first partials. Okay, and then we'll talk about the second partials. So go ahead and pause and answer the question. And then when you come back, here are the answers that we should have gotten. Okay. And if you're not understanding, pause, wrap your brain around that one. Okay. Now that those will be all of our first partial derivatives. Now again, we have 4 second partials that we could come up with. Okay, so partial of x with respect to x and then x again. So we're going to take this guy and take his derivative again with respect to x. So 6x plus 2y cubed. Okay, and then for the second one, we would take our partial with respect to x and now take it with respect to y. So we would be taking this guy again, but treating the x's as constants. So that first term would go away. The second term would be 6xy squared. Okay. Now we're going to move over. Okay. Both of these show that you take the partial with respect to y first. Okay. The top one, though, now we do it with respect to x. So we'd have 6xy squared minus 0. The second one we do with respect to y. So 6x squared y minus 4. Okay. You may have noticed something here. 2 of these are the same, right? That is Clairaut's theorem. French mathematician, is it Alexi or Alexis? Alexis, I think. Clairaut's theorem is basically that mixed partials are the same. Okay, so your fxy equals fyx. Okay, and in fact, it works for all higher order derivatives. Okay, so I could keep going. Like if I wanted to take this one, fxyx. Okay, that tells me to take my partial with respect to x first, then with respect to y, and now do it with respect to x again. So I'd have 6y squared. Okay. Notice if I take fxxy, so take your fxx and then do that with respect to y, I'd have 6y squared. Okay. I could also do fyxx, which is also 6y squared. Okay. So notice any combination there, as long as it's 2 x's and a y, got me the same answer. That's Clairaut's theorem. It works more than just the second partials. Any higher order partial derivative like that, that's going to work for. Okay, that's just kind of fun. So, if you had done all kinds of work to find, I wouldn't do this to you, but let's say that you had a problem where I gave you a function of x and y, and I had, it was a big complicated expression. I said, all right, I want you to find f, x, x, y, y, x. And you did all this work and you found it. And I said, haha, I'm going to be evil now. And I want you to find f, y, y, x, 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 x. Okay? You don't have to start all over again because it would be the same as f, x, x, y, y, x, x. You just take what you've already done and do one more partial and you'd get the same answer. Okay? We are just about done. The one thing that I want to add here, and this is getting into some kind of pretty advanced stuff. Okay, so we're looking at some partial differential equations. So once you get past Calc 3, linear algebra, you're going to have a differential equations class, which actually we'll get to. Okay, there are some very common partial differential equations. Remember, differential equation just means it's an equation with a derivative in it. That's it. So there are a few common partial differential equations that are used in very advanced math classes. You're not going to have to come up with these yet or anything like that, but Laplace's theorem or equation. Okay, if u is a function of x and y, that should be a Okay, so u is some function of x and y. Laplace's equation. If u is a function that makes this true. Okay, so there's specific types of functions where this is true, and you'd use Laplace's equation for it. We have the wave equation. This is a good one. U is a function of both time and distance, t and x. A wave equation can be used to model like the vibration in a string. It's a function of both how much time has passed since that wave has been created and the distance you are from where the wave was created. So you can think of like plucking a guitar string. How much that string vibrates is a function of how far it is from your finger and how much time since your finger plucked it. Okay, that's kind of a cool one. Your second partial of u with respect to t is equal to some constant, and we square the constant just because it works out better. And then dx squared. And that can be also in more than one dimension. We can also have something like it's not only a function of distance, in one dimension, but it could also be where it is in the y direction and where it is in the z direction. So and even more than that, if you want to get into some really complex abstract stuff, okay, and get that. And then we also have the heat equation, which is similar to the wave equation, but the first one is not a partial. Oops, I just said, or it's not a higher order. Okay, you can think about like heat in a rod is how this is often used. This one can also be more than one dimension. A is not squared in this one just because the math works out easier. But this one too, u is a function of t and x. But in this case, it's like where a heat source is and how much time has passed since the heat source began and how far down like the rod you are. And this one too can also be more than one dimension too, just, similar to this guy. Okay, so those are just some common partial differential equations that are going to be used in some advanced math classes. We're just going to do a quick problem using one of them. We're going to show that uxt is equals sine of x minus at satisfies the wave equation. So if you guys remember, when you did differential equations in calculus and in AB, you always had separable differential equations, and then you would separate and integrate and solve for the function that was a solution to that differential equation. Okay, it's definitely trickier now. They're just going to give you a function, show that it satisfies the differential equation. Okay, and again, your wave equation is d squared u over dt squared equals a squared d squared u over dx squared. Okay, so du dt, okay, so the derivative of our function with respect to t would be sine, I'm sorry, derivative of sine, so it would be the cosine of x minus at, and that whole thing times negative a. Okay, so with your chain rule. Second derivative then, okay, would be derivative of sine is cosine, derivative of cosine is negative sine. So we're back to a sine x minus at times negative a. So it would be negative a squared sine x minus at. Okay, we took the derivative first with respect to t and then again with respect to t. If that was a little too fast for you, I would encourage you to pause, rewind, and just kind of go through it again. Now we need du dx, right? So du dx would be, again, cosine of x minus at, but then just times 1, right? The derivative of the inside, if at is a constant, the derivative of x is just 1. And so then we can take the second derivative of that, which would be negative sine x minus at times 1. We're good. Okay, so now we want to show that this is true. Okay, so our d squared u dt squared, negative a squared sine of x minus at. Okay, so this is this. Okay, and that should equal, pen's freezing up again, a squared times second partial of u with respect to x, right? Okay. Okay, so that should equal negative sine of x minus at. Okay, and so we've got it, negative a squared sine x minus at. So we just showed that that function, where'd it go? This function is a solution to the wave equation. Okay, and that is it for 11.3.